Last lesson we said projection methods build brand new features by blending the old ones. The most famous of them all is PCA, Principal Component Analysis. It sounds intimidating, but seen in pictures it is wonderfully simple. Let's build it up. Start with a cloud of data described by two features. Notice it isn't a shapeless blob, it stretches along a diagonal. That stretch is the story of the data. This is the direction in which the points really differ. PCA's first job is to find that direction of greatest spread. Imagine spinning a line through the center and measuring how spread out the points are along it. The line where the spread is largest is the first principal component, PC1. It captures more of the variation than any other single direction. The second principal component, PC2, is the direction of the next most spread, with one rule. It must be perpendicular to the first. Here, that's the short axis across the cloud. Together, PC1 and PC2 are a fresh pair of axes, custom-built to match the shape of this data. And that's the heart of PCA. It simply rotates the axes to line up with the data's own directions. The points haven't moved at all. We've only redescribed them, no longer by the original two features, but by how far they lie along PC1 and PC2. Now we reduce. Since PC1 holds most of the spread, let's keep only PC1 and drop PC2. We project every point straight onto the PC1 line, sliding it to its nearest spot on that axis. Two features have become one, yet the points still spread out in almost the same order. We shed a dimension and kept the essence. How much did we actually keep? PCA tells us exactly, through the explained variance ratio. Here PC1 explains about 90% of the variation, and PC2 only 10%. So dropping PC2 costs us just 10%. The rule of thumb, keep enough components to reach around 95% and discard the rest. The real magic comes with high-dimensional data. Take 20 features you could never plot, and ask PCA for the top 2 components. It squeezes all 20 down to 2, and suddenly you can draw the data on a flat scatter, and often the clusters leap right out at you. That is how we finally see high-dimensional data. In scikit-learn it's 3 lines. Create a PCA with 2 components, transform your data, and you get back a 2-column array. The attribute explained variance ratio _ reports how much each component kept, your evidence that 2 dimensions were enough. To recap, PCA finds the directions of greatest spread, the principal components, and rotates the axes to match them. Keeping the top few components and projecting onto them reduces dimensions while preserving most of the variance, which the explained variance ratio measures. It's the go-to tool for visualizing and compressing high-dimensional data. Next, we hunt for the odd ones out, anomaly detection.